Get ready for some crazy stuff in these next few videos. Now, the nucleus is great. It's got the protons, it's got the neutrons, it's involved in nuclear crazy reactions, which we'll talk about later. But to be honest with you, the electrons are my favorite part of the atom. The electrons are involved in chemical bonding. They're involved in chemical reactions, which is what we usually do in this lab. We won't do any nuclear reactions, hopefully, in our lab. So we really want to get a good snapshot as to where all the electrons are found and what their properties might be. That's going to allow us to predict chemical bonding. Will these atoms bond together? Will they form a compound? And if they do, what kind of properties will they have? And from there we can predict what kind of chemical reactions might occur. That's the good stuff. So we're going to use something called quantum numbers. Whoa, crazy. Quantum numbers are a set of symbols that are kind of like an address. They're used to locate an electron to the best of our ability. We're trying to locate moving electrons, so there's never a way that we can pinpoint the exact target location of a moving electron, but this is about the best we can do. So I like to think about these quantum numbers as like an address. We're trying to identify the region where this electron is most likely to be found. Kind of like your house. Your house would be the region where you are most likely to be found, I guess outside of school. But within that house, you're always moving. You could be upstairs, downstairs, I don't know. An electron house is called an orbital. Orbital, there it is. This really is just a region where there's a high probability of finding an electron. Now this here, the circular region, is supposed to show electron density. The electron is moving throughout this region, but like 99% of the time, I can find the electron in this region. So it's like the house. Now, are there a few little dots outside of the circle? Sure. So if I were to take a snapshot of this electron as it moves over time, yeah, on occasion it's outside of this region, this orbital. But again, 99% of the time, probably even better than that, we can find the electron in this target region called an orbital. Alright, some more specifics. The first quantum number, the first symbol in the address of an electron, identifies the energy level. Okay, that's cool. We know there are energy levels. More specifically, by saying the energy level, I like to say the distance from the nucleus. The energy level really gives me an idea how close to the nucleus is that particular electron. This will be a symbol from 1 to 7. Here we have 1, 2, 3, 4, etc. As of today, with all the elements that have been discovered, approximately 120. The furthest energy level known is 7. Now ask me in a month and there could be energy level 8. There's constantly research trying to develop new synthetic elements from nuclear fusion reactions. And so, yeah, I have no doubt someday we're going to have elements that fill 8, 9, maybe 10 energy levels. But for now, we'll go 1 through 7. Okay, so this makes some sense. If we kind of say that the nucleus would be in the center, and for nucleus, I'm just going to do a little positive. I'll do a little positive circle. The nucleus is in the middle. And I guess same thing with this big boy. I'll make it red. So there's a little positive nucleus in the middle. So energy level 1, or here they have it listed as N equals 1. N just stands for the energy level. Level 1 means the electron is pretty close to the nucleus. And we also know that level 1 would be low energy. So this would be a low energy electron. Kind of like this picture. Again, if I could take a snapshot, kind of plotting the movement of this electron over time, and I superimpose all those pictures on one another, this electron is staying pretty darn close to the nucleus. Level 1. Level 2, the electron is further from the nucleus. Level 3, further yet. Now there seems to be a lot of electron activity further from the nucleus. Level 4, level 5, and so on. And again, as we go further from the nucleus, this would be higher energy. So in these quantum numbers, this set of symbols that identify the location of an electron, the first quantum number will be a number from 1 to 7, identifying the energy level and on average the distance from the nucleus. Alright, that's not so bad, right? We're cruising. We're ready for the second quantum number. Here's actually where it gets a little wild. Alright, so these orbitals are three-dimensional regions around the nucleus where we have a high probability of finding an electron. Their shape is really determined experimentally. Where is this electron moving? And over time, where do I have a good chance of finding that electron? So when we study electron movement, we come up with different shapes of orbitals. They seem to follow like different paths. These electrons seem to follow different paths over time. And again, we have to picture these as three-dimensional. The first shape of orbital is called an S orbital. So the second quantum number identifies the shape of the orbital. Now this is kind of goofy, but the shape of the orbital is noted by letters, not numbers. So they're called quantum numbers, but yet they're really letters. We'll deal with it. S orbitals, they're low energy orbitals, and they are sphere-shaped. So everybody always gets this one right. S orbitals are sphere-shaped. There is an S orbital in every energy level, and there's only one. Every energy level starts with an S orbital, a spherical region around the nucleus where you have a good chance of finding an electron. Each S orbital can hold up to 2 electrons, maximum 2 electrons. Okay, so now look at this. Here's a good, I guess, 2-dimensional picture. Picture these as like balls, a 3-dimensional sphere. The nucleus is in the center. Positive nucleus. Positive nucleus. The 1s orbital means that there's an s orbital in the first energy level. The 1 stands for the first energy level. The first energy level is close to the nucleus. It's a pretty small orbital. It's a small little electron house. Look at the 2s. It's a little bigger. The second energy level will also have an s orbital, a sphere-shaped orbital. A sphere region where you can find electrons. But notice that it's a little bigger, because on average the second energy level is farther from the nucleus. So now in the 2s, the electrons have a little more space. They can zip around in this bigger orbital, which allows them to be a little bit further from the nucleus. For kicks, what if a question said, here's the 1s, here's the 2s. Draw a picture of the 3s orbital. Well, if it's an s orbital, it's a spherical orbital, sphere-shaped. 3s means third energy level. So it's going to be a little bit farther from the nucleus, which means it's going to be a little bigger. So we would draw something that looks like this. And we'd say this is the 3s. It'll have a nucleus in the middle, We'll just draw kind of a little positive nucleus. The nucleus is positive, right? It's just got protons and neutrons, and the neutrons are neutral. So here's kind of the difference. First energy level, second energy level, third energy level, and beyond. I mean, this is going to go all the way up to 7s. The 7s is just a giant sphere orbital. They're all the same shape. The difference is just the size. As you increase in energy level, the electrons are further from the nucleus. Now here's the other thing that will always stay the same. 2 electrons. These S orbitals can all hold 2 electrons. Now within the orbital, we really don't know exactly where they are. We just know that within this region, we have a high probability of finding electrons. There could be a maximum of 2. I don't know, maybe there's 1, 2. Maybe they're both up in the top. Maybe they're both over there. I don't know. Within the orbital, electrons are free to move. But by saying the 3s orbital, I know that I'm looking for electrons in the 3rd energy level traveling in this spherical region, 3-dimensional region around the nucleus. Pretty wild, huh? Nobody ever gets the s orbitals wrong. Now when we come to class, I'll kind of show you some 3-dimensional models of these orbitals as well. Alright, here's the next one. The next shape of orbital is called a P-orbital. Again, these are called quantum numbers, but I get it's kind of weird that the quantum number is here actually a letter. You'll get it. P-orbitals are a little bit bigger than S orbitals. They have kind of this dumbbell shape, they call it. Kind of a figure 8, there's like 2 loops, or 2 lobes to these dumbbell-shaped P-orbitals. Now, because they are greater in energy than the S orbitals, you won't find these until the 2nd energy level. So as we start like putting these quantum numbers together, there is no such thing as a 1p. Nope. No such thing as a 1p. But there is 2p all the way up to 7p. These p orbitals are too big and they carry too much energy. You will not find p orbitals in the 1st energy level. That's a small energy level and it's very low energy. Okay, so now there are 3 of them. There are 3 p orbitals in every energy level, not the 1st. And every orbital can have 2 electrons, which can give you a maximum of 6. Alright, so check these things out. I love the p orbitals. They're actually my favorites. The p orbitals look the same. All 3 of the p orbitals look the exact same thing. The only difference is just the way that they lie in space. They're just on a little different axis. One's kind of up and down, one's coming right at you, one's side to side. That's like the little px, py, pz. They're just trying to show they're the exact same orbital. They have the exact same shape, the same energy. They're just lying in a little different axis in space. Okay, so we have to picture these as, again, 3-dimensional. There's a positive nucleus in the middle. So here's kind of the positive nucleus. This time the electrons seem to be in like 2 different regions around the nucleus, which is what gives us this dumbbell or lobed shape. Now again, all these orbitals can hold a maximum of 2 electrons, but we don't exactly know where those 2 electrons are. They're free to move within this orbital. There could be an electron on the top, an electron on the bottom. Cool. Maybe they're both in the same lobe. They could do that. Okay, maybe they're on opposite ends. That's the uncertainty. Within your house, you are constantly moving. Within an orbital, the electrons are constantly moving. But if we give these symbols, these quantum numbers, we have a good chance of finding the electrons. It's the best chance we have. Okay, now let's get a little more specific. What if I say these are like 2p? Let's put these symbols together, 2p. These are p orbitals in the second energy level. Okay, cool. Since there are a total of 3 orbitals, and each can hold 2 electrons, that's where I get the maximum of 6. 2, 4, 6. And now what if they said, sketch a 3p orbital? How would a 3p orbital look the same? How would a 3p orbital look different? And you'd say, piece of cake. If this is a 2p orbital, the 3p is very similar. It's just a little bigger. So maybe this is a 3p. It's the exact same shape, but it's going to be a little bigger because the third energy level is farther from the nucleus. So now the electrons have more space to move. But they're still going to move in kind of the same path, the same shaped orbital. These are going to be a little bit higher in energy than a 2p. But the same general shape, just a little bigger. That's good stuff. Okay, so we have the S orbitals, those are spheres. Those are found in every energy level. They're low energy spheres. Every level, 1 through 7, starts with an S. The p orbitals are not found until the second because they're a little bigger, a little higher in energy. And then finally, the last type of orbital that we will deal with are D-orbitals. Holy buckets, look at these crazy orbitals. Okay, so these are even higher energy, even higher than the P's. Which is why you won't find these till the third energy level. They have too much energy for the first energy level and the second. You won't find these crazy D orbitals until the third. So there is no such thing as 1D or 2D. They'll try to trick you like that on a test or quiz. They might say, like, which of the following would never be a valid quantum number? The D orbitals, look at them, they're huge. They have 4 lobes. They're too big and too high energy. You will not find them in the first or the second. But you will find D orbitals in levels 3 through 7. So 3D, 4D, 5D, up to 7D. That is all valid. There are 5 of them. Most of them look the same. They're these 4-lobed regions. So again, it's like you'd have a positive nucleus in the middle. It's just like, I don't know, maybe it's like a 4-bedroom apartment or something. There's just more compartments. There's more rooms where you could find these electrons. Positive nucleus in the middle. The electrons seem to hang out in these 4 regions around the nucleus. There is one kind of goofball D orbital, and it is called the donut orbital. This guy, nucleus in the middle. 2 of the lobes seem to kind of join in a ring around the center. Even though its shape is a little bit different, it's still not found until the 3rd energy level, and it carries the exact same amount of energy as all the rest of them. So we say that there are 5 possible D orbitals. And again, since these D orbitals can each have 2 electrons, we can have a total of 10 in all of the D orbitals combined. And so again, we don't know exactly where those 2 electrons might be. Maybe there's one up top. I don't know, maybe there's one in the donut. Maybe they're across from each other. They're on the top. I don't know, one's front and back. That we'll never know for sure. The electrons are free to move at all times. But within this region, we have a really good chance of finding at least 1, maximum of 2 electrons per orbital. So we put these quantum numbers together to show the energy level and the shape of the orbital. And again, let's say that these are 3Ds. So let's say this is a 3D orbital. And then they say, what would a 4D orbital look like? Exact same thing, just bigger. The electrons would follow the same general path. The 4D would just mean that it's the fourth energy level. So the electrons, on average, could be further from the nucleus.